As you know, both shock and vibration are prime culprits in many drilling problems. Today we are going to discuss how to minimize their effects and thereby improve drilling performance. Shock in a drilling environment is the sudden input of energy from impacts of the bit, BHA or drill pipe with the wellbore. Vibrations can result from the shocks. Rapid and continuous vibrations result in fatiguing of the drill string connections to the point of twisting off. This is why many drill string failures are the result of cumulative fatigue due to vibration and have regular inspection periods. Shocks are measured in G's by an accelerometer. 1 G equals the force of gravity. Shock magnitudes registered via downhole tools can exceed 200 G's. The severity of the shock depends on three parameters. 1. The magnitude of the shock. 2. The duration or length of time of the shock. And 3. The frequency or number of shocks. Magnitude is the force the tool sees when it impacts the borehole wall. Duration measures how long the shock lasts in seconds. Frequency is the number of times the tool sees a shock greater than the accelerometer's threshold. Shock and vibration and poor drilling mechanics can adversely affect ROP, slowing the drilling process. So how do we detect potentially harmful shock and vibration? Surface and downhole data in both depth and time formats are used to diagnose downhole conditions. Looking at the drill string and bit after the run will also help to determine the severity and type of shock and vibration. Schlumberger measures lateral shocks in all of their tools. These tools have shock sensors that measure lateral vibration shocks with magnitudes greater than 50 Gs. Our discussion will look into 6 BHA dynamic motions: axial, lateral, torsional, BHA whirl, stick slip, and eccentric. These can exist separately or can be present together. Proper identification of the vibration mode is essential in order to recommend the correct cure. Axial shocks arise from movement of the drill string along the axis of the drill string. In the most severe form, it is sometimes referred to as bit hopping or bit bounce. However, in most cases, there is not enough force to allow the drill string to come off bottom and bounce. Instead, shocks are transmitted up the drill string, which harmonically increases and decreases the weight on bit. The consequences of axial shocks could be broken bit teeth, damaged downhole tools, and slowed ROP. Lateral shocks result from lateral motion of the BHA from one side of the wellbore to the other, causing it to bang randomly against the sides of the borehole wall. Torsional shocks result from the momentary slowing down or stopping of the drill string. This occurs when the bit digs into the formation deeply enough to slow it down relative to the drill string, or when a stabilizer digs into the formation. This causes a winding effect in the drill string, which can fatigue the drill string and BHA. BHA whirl is very complex and exists as a result of understabilized drill string and forces acting upon the BHA, such as rotating close to a resonant RPM or enlarged borehole. Whirl occurs most frequently, but is not limited to, near vertical wells. It occurs when there is enough sideways or lateral movement in the BHA for it to contact the wellbore wall. In the video, we see a rolling shock test where BHA components mounted horizontally are anchored at each end and rotated. In the center, a 10.5-inch steel casing ring is attached to simulate the borehole. There are three main types of BHA whirl: forward, backward, and chaotic whirl. Forward whirl is when the BHA rubs the formation along the same part of the collar as the drill string rotates. If the formation is abrasive, excessive wear will occur along the part of the collar that rubs the formation. This wear is seen as flat spots on one side of the collar, or as a single worn blade of a stabilizer. In forward whirl, the BHA still rotates in the same direction as the drill string. Forward whirl can destroy bits and BHAs. Backward whirl is very similar to forward whirl, except friction between the formation and BHA is greater. This increased friction results in increased torque on the BHA, which causes the BHA to rotate in the opposite direction of the rotation of the drill string. If whirling is backwards, then the collar connections can flex and fatigue at a very fast rate, resulting in accelerated fatigue cracking, washouts, and possible twist-offs. In chaotic whirl, there is no preferential side of the collars or BHA contacting the formation. The torque will be above average along with the lateral vibrations and shocks. Chaotic whirl can occur when changing rotary RPM to try and address forward or backward whirl. Bit whirl is associated with PDC bits because of their aggressive side-cutting action in harder rocks and near vertical holes. It is caused by non-symmetric cutting action of a real formation that displaces the bit from its center of rotation and then allows the bit to move. Verification of shock and vibration can often be obtained by examining the bit after a trip. When dealing with BHA whirl, it is sometimes necessary to stop drilling completely to cure it, depending on the severity of the shocks and difficulties with drilling. Stick slip is the non-uniform rotation of the drill string. This is the rotational slowing down and acceleration of the BHA. In extreme cases, the BHA can stop or even reverse its direction. During drilling, friction builds up, causing the BHA to momentarily turn at a slower rate than the surface pipe, or even stop. As this happens, the string stores the energy imparted by the rotary or top drive in the drill string. As this energy builds up, the friction-slowing BHA rotation will be overcome. When the stored energy is released, the BHA has to catch up to the rotary table. This results in a rapid increase in BHA rotation. Since it has now gone beyond the number of rotations the rotary has made, it will now spin backwards for a short period to become in step with the rotary RPM. When this happens, an inadvertent unscrewing of a connection can occur. Our review of shock and vibration effects in drilling is a good starting point for your understanding of the issues raised by these phenomena in the drilling environment. Schlumberger wants you to develop your knowledge of these issues, how to detect them, and how to mitigate them. These different types of shock occur simultaneously, creating serious drilling problems, which often require drilling to stop and then restart. Careful planning, execution, and post-job analysis will often reduce the risk of these shock and vibration hazards. We hope this presentation will assist you in this endeavor. Thanks for your attention.